calculate the theoretical. That point.
No, by calculate from theoretical values means that you know the bias points, you know GM, you know the gain and all, right, from the DC simulations. So from there, you would expect a ICMR, some value of ICMR, some range of ICMR.
Okay, and also there is written as verify with simulation.
Yeah, so that is simple, right? You just sweep your VCM and check when the transistors go out of linear.
That point.
Yeah, that's all it means. Any other questions regarding project? Any confusion? No? Okay, fine. So in the last class, I realized that we introduced stability in kind of an ad hoc manner. And that was kind of done purposefully because we wanted to show you, at least with the background knowledge that you have, that things probably are not as hunky-dory as what you might think if you want to put multiple GMs in multiple high gain stages in cascade, right? So so in this class, what I would like to do, I would like to slightly approach the problem in a slightly more formalized manner. Still, it is, if you want to fully appreciate stability in a closed loop system, then in a sense that itself is a full course. We don't have that luxury. So what I'll do, I'll just try to put the existing knowledge that we have, and I'll assume that you have taken at least one control system course in your UGs. So I'll try to leverage that, and let's see where we proceed. Okay, so so to start off, we are comfortable with Bode plots, but there is one more thing called Nyquist plot, right? So what is a Nyquist plot? The genesis of a Nyquist plot is as follows. So if you have, let's say, have a function f of s, where s is sigma plus j omega, which essentially means that it's a complex number, then what we will do is so since s is a complex number, f of s will also be a complex variable, a complex function. So how do you plot a complex function? Obviously, you cannot, in a two-dimensional domain, you cannot really plot a three-dimensional function. I mean, you can, but it requires a lot of skills, which I don't have. So so what we generally do is we say that, okay, so we'll take one point on this S plane. Let's say this is the S plane where sigma, this is omega. And let's say this is real of Fs. This is imaginary of Fs. So what I'll do, I will take, let's say, one point on this S, this is the S domain, and this is F domain. If we take one single point on this S domain and find out what will be the corresponding Fs, it will probably map to one point here, right? Similarly, if I take another point here, it may be, it probably maps to another point here. So I can keep on finding, keep on filling the right-hand side plot by taking essentially all plots, all possible points in the S domain, and I will get a contour. So I will get a and if I keep on doing that, and let's say I choose any arbitrary contour on the S domain, and I say that what I'll do, I will take all points in this circle. So as it turns out, I mean, it's also quite intuitive that the fact that on the F domain, you will also have some sort of a closed shape. And as it turns out, if the direction of the direction in which the closed shape will get rotated in the Fs plane, in the F domain, is the same direction in which you are taking the points on the S domain. So what I mean by that, if this is clockwise, this contour will also get closed in a clockwise manner. Okay. So again, this is also just a statement that I made, but there is rigorous mathematical proof. This is basically Cauchy's theorem. You can go and you can check it out. So now, how come? I mean, why is this useful to us? This is useful to us because ultimately what we are essentially looking for is whether our system is stable or not. When we say we are looking for whether our system is stable or not, what we are essentially saying, we know that our system is of this form, L by 1 plus L, where L of S is a complex number. Okay. And if the system is stable, then 1 plus L of S will not have roots in the right hand plane, right? If this is for stability. So because we want to ensure that 1 plus L of S does not have roots on the right hand plane, which means we'll have to do something. We'll have to essentially find a contour which encompasses the entire right half plane, and then figure out whether the roots actually lie in this contour or not. So that's essentially the premise. So if I have to go into that premise, I'll have to then first find out a way to figure out how do I know whether the root lies inside a contour or not, any contour. Okay. So if I do the same thing here, let's say this is S domain again, this is sigma j omega. This is real Fs. This is imaginary Fs. So going by the same notation, same logic that we did that we used in the previous example, let's say I say that you have a root. Let's say this point S naught is a root of the function Fs. So where does this map on the F plane? Pardon? Yeah, so root means what? F of S goes to 0. So when I say S naught is a root, which means F of S naught is 0. So this maps to the origin. Okay. So one might say that, hey, I mean, I keep on I keep on tracing the entire S domain, right? I keep on tracing the entire S domain for all possible values of S, infinite possible values of S, and see where the exact roots are, right? So that is one possible way of arguing. But obviously you understand this is not a very feasible way of arguing, because essentially you'll have to sweep the entire S plane, which has infinite points. So since this is not possible, we need a slightly more smarter solution. And as it turns out, Cauchy again comes to our help. What he essentially says that you don't have to know the exact location of the root. What I need to know is that, let's say I find a contour, any contour, and I start from any point on this contour. I start from any point of this contour and I come back. And if the root exists within this contour, then I will have another contour on F of S, F domain, which encircles the origin. Right? So intuitively, again, it should make sense, because if this contour in the S domain would have passed through the root, the corresponding plot in the F domain also would have passed through the root. Right? So if I go slightly away from the root, so this contour will also encircle the root. Again, these are all intuitions, but this is not mathematics, right? For mathematical derivation, you have to go into Cauchy's theorem. So now, if we take this at face value, if we take this assumption as face value, what are we looking for? What we are interested into seeing whether there is any root of the closed loop transfer function on the right hand side, right? So we'll have to ensure that no roots of 1 plus L is present in RHP. Okay. So if that is the case, what is my, as a designer, what is the contour that I should choose to ensure that, to check whether the roots are there or not in the RHP? It should be the entire RHP, right? So there are now, the argument comes, you can choose, I mean, how do you choose an entire RHP? You can choose it in many different ways. One convenient way is to say, I will start from the center. I will go all the way to infinity, and I will just make a semicircle, come back and go back. Okay. Fine. And then what I will see, I will just see whether there is any possible encirclement of this. By the way, this direction also matters. If you do this encirclement in the clockwise direction in the S domain, it will be on the clockwise on the F domain also. So if there is one encirclement of the zero of the origin in the F domain, it will tell me that there is one pole. Now Cauchy doesn't really stop here. He says that if there are multiple poles, let's say you have two poles on this contour, then as it turns out, you will encircle this origin twice. In the same direction. Okay.
True when 0 is not there.
This is true when 0 is not there. So again, I mean, a caveat is that we are only dealing with all pole system in this, right? So that's why I made that statement. So now this essentially gives us a good handle to figure out whether we don't need to sweep across. We need not plot all S domain, all points in the S domain. We can choose a contour and then make a conclusion. Okay. If that is the case, so how does it tie up with our narrative of stability? So let's assume. Okay, so even before one, I jumped one step. So now what we are interested in is to figure out whether 1 plus L doesn't have any root on the whether it doesn't have any encirclement of 0. Now the Nyquist came and said that why 1 plus L? Why should I bother about 1 plus L having encirclement around 0? If all we are interested in L is L, because loop gain is easier to figure out, then I would say that I would try to figure out if L doesn't have any encirclement over the -1 point, -10 point. That essentially is your Nyquist criteria. So what this entire action that was concentrated around -1 gets shifted to, sorry, that was concentrated in the origin gets shifted to -10. Okay. So essentially now what we are saying is this is the S plane, this is the L plane. So what I will do, I will start from origin, go all the way to infinity, come back, go this way, and I will check whether there is any encirclement of -10 point or not. If the contour looks like this, then I know it's unstable. This is unstable. If my contour looks like somewhat like this, then I know this is stable. Because in one case you have encirclement, in another case you don't. Okay. Fine. So now Nyquist is great, but the issue is that it's slightly difficult to visualize because it's difficult to visualize at what frequency point the curve is at any point of the plot, right? Because if I tell you what is the frequency at this point, you will not know, because x-axis is not frequency in this plane. So that's why Bode comes in. So in Bode, you know exactly at what frequency what lies. So you plot Bode and Nyquist together to get a fair understanding. So let's do that. So let's start off with the easiest one, that is the first order system. Let's assume you have L of S to be equal to A0 by 1 plus S by P1. So this is Bode. So this is magnitude of L. So you get constant gain of A0 till P1, and then it rolls off at -20 per decade. Similarly, in the phase domain, angle, you start off with 0, then you hit minus 45 at P1, and then at omega equal to infinity, you settle at minus pi by 2. Okay, so the corresponding Nyquist will be, so this is L, this is real L. So when I start from omega equal to 0, what will be, where am I at in the Nyquist plot? In the right hand side plot? It will be A0, right? So L of 0 is A0. So A0, assuming it's a very large number, it should be large real number. It should be far away on the x-axis, right? On the real L. So somewhere, let's say here. So now if I keep on increasing omega, right? If I keep on increasing omega, and obviously mod of L decreases. It's not evident in the Bode plot because Bode plots are straight line segments. But in reality, you will see that obviously denominator increases, so this thing will decrease. I mean, the magnitude plot will decrease. The magnitude of L will decrease, which means it will start coming closer towards the origin. Okay, so now it can come closer towards the origin in many ways, right? So it can come this way, it can come that way. So which route will it prefer? I mean, do you think it will choose? Negative, right? Because it goes in a negative direction. The phase is, I mean, from the Bode it is evident that I am going in a negative phase direction, which means I should be somewhere on the bottom side, right? So fine, so it goes somewhere like this. So now things become slightly hand wavy because I don't know where exactly is what, right? Because you need a computer to tell you exactly at what point you are at in the Nyquist plot. So for hand calculations, what we say is that we will just look into the critical points and see whether we are far away from stability, near to stability, near to that critical encirclement point or no, or what. So what is the critical encircle point in our case? This is this point, minus 1, 0. Okay. So to figure out whether we are near to that or not, we'll have to make one observation, and the observation is the fact that this is a monotonically decreasing function, right? Mod of L is a monotonically decreasing function, which means once it goes, let's say, I draw a circle with radius 1. Once it goes inside the circle, from whatever direction, it cannot come out. Monotonically decreasing means it has to keep on going in its own direction. So we'll have to figure out at what point it enters the circle. That becomes a critical point for us to check. If I am entering the circle far away from the minus 1, 0 point, then I know that there is no way it is going to reach there because it's a monotonically decreasing function. So how will you figure out where it enters? And which is that? What is that value? That is omega u loop at which it will enter, right? At omega u loop, your gain is 1, right? So what is that omega u loop value? Approximation using Bode approximation that you get. Pardon? A0 times P1, right? So because you set, I mean, using Bode approximation, when you are far away from P1, you basically become A0 by S P1. This you set to 1, right? So your corresponding omega u loop is A0 times P1. So at A0 times P1, what is the phase? Minus pi by 4, right? So clearly you are somewhere here. You are minus 45 degree, right? You are far away from minus 1, 0 point, so you don't have to bother. So you enter, and you also know that at omega equal to infinity, you are reaching 0, but with what angle? Minus pi by 2, which means you are reaching 0 vertically from the bottom side. So something, your curve will somewhat look like this. So this is when you are going from 0 to infinity, omega going from 0 to infinity. Okay. So, and also we know that these are symmetric with respect to omega, which means whatever is happening from 0 to infinity will happen from minus infinity to 0 also, which means this plot wraps around when on the other side. So when it wraps around, this essentially will become something like this. Okay. And why am I not bothered about this? I mean, 0 to infinity is this, so minus infinity to 0 is this. What about this contour? We are not bothered because that is essentially 0, right? Even though that's this infinite round in the S domain, in the L domain, is essentially one single point of 0. So you don't really bother. So that's what the beauty of your Nyquist plot is. So you can basically ignore many of the things that might seem tedious. Okay. So this clearly is a first order system, clearly stable, no surprise. So now let's go to a second order system. So let's assume we have a second order system where first pole is obviously somewhere. Let's assume the second pole is beyond the omega u loop. Okay, so this is omega u loop. Second pole is beyond omega u loop. So corresponding phasor will be, it will start from 0. Around P1, you'll have minus pi by 4. Something like this, then something like this. And it will settle with minus pi. Okay. So corresponding Nyquist should look like as far as the DC picture is concerned, is still the same. You have large gain right on the right hand side, and then you again start decreasing. Okay. So, but now where do you enter? At what angle do you enter omega u loop? Is it? So this is here. The way we, I mean, so okay, so let me draw it a slightly neater picture. So this is minus pi by 4. Let's assume this is minus pi by 4. I don't even have to assume that, right? So if it's way, if P1 is, let's say, let me draw it this way. If P1 is at very low frequency, so then it reaches minus pi by 2 comfortably, then goes like this. Okay, so from this plot, where do you think I'll be cutting? At what angle I'll be cutting the this? Yeah, it's clearly, I mean, on the other side of minus pi by 2. So which means I'll be cutting it somewhere here. I mean, how far you will go depends on where this P2 is, right? So let's assume that you are cutting it here, which means you go something like this, and so on. And if you draw the other half, so it becomes something like this. So clearly, you were, I mean, the way I have drawn, you are away from that minus 1, 0 point, so you are safe. So now the fun starts. So what happens if P2 moves, right? What happens if P2 moves? And let's assume that P2 is moving in such a way that it comes somewhere over here. Okay. So if P2 comes somewhere below the current UGB, obviously the UGB will then change. So it will become something like this. So if this is the case, how do you think the original Nyquist plot will get modified? See, all we are interested into is to figure out where I am cutting the unit circle. It will cut. No, why will it cut? Will it ever cross? Will it ever cross? Will it ever cross this and encircle through that point? It will never, because you always maximum in a second order system, maximum phase delay is -5. So it cannot ever go up in 1/2. Okay. So, but what happens is that, I mean, but I presume you understood this point, that if I draw the phase, phase diagram of in the body, so this will largely remain same here, but now it will start to drop, right? So, and it will reach omega u loop somewhere here, and clearly the phase at this point is much worse than the phase at that point, which means I am moving closer and closer to -10 point. So in this case, it will probably look something like this. So, so essentially, I mean, the moot point is that you are getting closer and closer to the, I mean, dreaded -10 point, that is the instability point. And so now we are in a position to define some margins, because it's not as if, I mean, when in a second order system, as you saw in the previous lecture, that if zeta is 0, then it's unstable, but zeta close to 0, rather zeta is 0, it's marginally stable because you will have an oscillation. But if zeta is even close to 0, you will have considerable ringing. It will go like this, right? And then finally settle, which is also not acceptable, right? Because you want the system to respond quickly but accurately, right? So there's no point having a very fast system which doesn't know where it's going. So that defeats the purpose. So essentially, essentially you would want to get a system which settles quickly and cleanly, which means you cannot be in a situation where zeta is very close to 0, which means zeta close to 0 in Nyquist plot is essentially cutting the -10 point. Okay. So if you now, what we are essentially saying is that we need to figure out how far we are from -10 point when we are cutting the unit circle. Okay, so that essentially is the margin, and that is what we call phase margin. So for example, in this case, I am cutting this -10 point at an angle, let's say of, I don't know, theta, whatever. Okay, so this theta is my, this theta, what is this theta telling me? This theta is essentially telling me if I give an excess phase lag to this system by an amount theta, then I will be cutting that -10 point and my system will become unstable. So which essentially is a backhanded way of saying I have a margin of theta before my system gets unstable. And theta is in phase domain, so we call it phase margin. Okay. So yes.
But this plot will never touch the -10 point.
Yeah. It will never. But this is only a second order system, right? So there's a reason we do this theta, because second order system, even you don't even need all these things. You can do brute force hand analysis.
So in the second order system can never be fully unstable, right?
It will never be. It can be at max become marginally unstable or marginally stable when zeta is 0, right?
Sir, another question, like, is there any point in the Nyquist plot where you can say that zeta is 1? Zeta is 0 means that is minus.
Yeah, definitely there is. So you tell me, what is the condition on zeta equal to 1 from previous lecture? There was a condition, right? So what was the condition of zeta? What was the expression of zeta? So this was the expression. And if I further assume that they are further apart, then zeta is essentially this. Right? So zeta equal to 1 means P2 equal to 4 times A naught P1. Right? So if you hit this condition, then you get zeta equal to 1. Okay, so that is a design variable which is in your control. Where did I go? Okay.
So that point explicitly you cannot see in the
Yeah, in Bode you can see that. In Nyquist is difficult to see, right? Because Nyquist you don't have this point-to-point frequency. You cannot see it visually. That becomes a problem. But what do you want to see? Do you want to see P2? Do you want to see P1? Do you want to see omega U loop? In Nyquist, you can figure out easily what is omega U loop point, right? So now what taking his lead, tell me if the system is stable, right? Let's say the system is in such a way that it was stable and P2 was beyond omega U loop. So can you tell me which side of the unit circle P2 lies, inside or outside? Inside, right?
High frequency mode.
Not only high frequency, see, when you are reaching P2, your gain has gone down below 1. So you are inside unit circle, right? So this is another way of arguing that, let's say I have another pole. So let me. So let's say P2 is somewhere here. Okay, so then you go like this. So let's say I have another pole which is beyond P2. Let's say I have another pole here. So where will that pole, how will that pole affect this Nyquist plot?
First of all, it will change the shape of this.
Forget about shape. Let's assume encircle. Yeah, so it will change the shape inside. So whatever change it will occur somewhere inside, right? But again, so that is again a crude approximation, because it's not as if it only changes inside. There will be slight change in the outside also, but you get the point, right? So most of the action is happening inside the unit circle, not at the region where you are cutting the unit circle, right? So which essentially means that if I have poles which are far beyond omega U loop, you don't really care. System will still be stable, right? Because you can have something like this. You can have this. It doesn't really matter. It will still be stable. So looking at the unit circle, one conclusion you can straight away draw is that if you end up with a system which is multipole, which you always will, you will always have a multipole system. It's not a problem as long as all poles other than single pole lies within the unit circle, which essentially means that the conclusion essentially is if all but one pole lies within unit circle, that is beyond UGB, our system is stable. Okay, is likely to be stable, because we have to put that caveat. Because you might say I'll put infinite number of poles inside, then incrementally it will keep on affecting the overall plot, and it might end up getting unstable. But in most cases, this is stable. But this statement is true only for all pole system. Why am I saying this all the time? This all pole system business is because if you have a zero, then it's possible the Nyquist plot, once it goes inside, it can also come back. By zero, I mean that if you have, let's say 1 plus S by Z or something like that, it is possible that it can, your numerator can increase after Z, right? So if you say all pole system, all real pole systems, everything, and you know that the magnitude of L of j omega will always decrease. But if you have something which invalidates that assumption, then you have a problem, right? So all we are doing here is dealing with all pole systems. So that is why this conclusion is broadly true. Okay. So this is for this is what we did for 2 pole, but now obviously you know what's coming, 3 pole. So let's say L of S is A naught by 1 plus S by P1 . So you will have something like this, mod of L. Start from 0. So then you cross 1 at certain angle, then you cross 0. Actually, it should be here, right? And ultimately you settle at minus 270, right? So when you have this minus 270 kind of, when the maximum phase is minus 270, then you are likely into trouble territory. Because if you are not careful, I know that I am reaching the 0 point at an angle of minus 270, which means I know that whatever happens, I am reaching it from this angle. And I know I am starting from here. So now there are multiple ways of reaching that point starting from this location in a monotonic manner. So I can go this way, I can go this way, and any way in between or somewhere, right? So clearly, if you go this way, you will be encircling, because if you close the, if you go from minus infinity to 0, then your plot will look something like this. So there is an encirclement. So you clearly don't want this. And from yesterday's or the last lecture, what do you think is the condition when I, let's say, just cut and then enter? What is A naught? Assuming P1, P2, P3 are all in the same location, what is the value of A naught? What was the maximum gain you were getting if you have, let's say, L of S to be for the system to become unstable, if this was the case? You look into last lecture and tell me. If you had a gain of 8, right? So if you have a gain of 8, which means this, your Nyquist plot would have started from somewhere here. This is 1, this is, let's say, 8. And if you had only a gain of 8, you would have cut this minus 1 0 point, and your system would have been unstable. And from monotonicity and all monotonic plots, monotonically decreasing phase, if you have gains which are on beyond 8, then you are clearly encircling and your system will become unstable. Okay. So now if you have, now the question is, how does Nyquist plot help us? Nyquist plot helps us in not only visualizing this, it also helps us in determining how far we are from this danger point, or how far we, let's say you have crossed this unit circle also, you have crossed this danger point also, how far we need to pull the system back. So that margin is essentially what we call it in terms of phase, we call it as phase margin. For example, in this purple plot, I know that I clearly see that I have crossed this unit circle, let's say at an angle theta. So I know that my phase margin is theta. If in the case of the green circle, I have overshot it, and which essentially means that I'll have a negative phase margin, right? Because whatever negative means in this case, this will be, let's say, minus alpha. Your phase margin will be minus alpha. The minus alpha phase margin is basically an indicating to you that it's not only unstable, you'll have to decrease the excess phase by amount alpha in order to make your system stable. Okay, make sense? Okay. So now, as I said, it's difficult to figure out exactly at what frequency what happens in Nyquist, but you see there is an analogy between Nyquist and Bode. So what we generally tend to do is to look at the Bode plot and then figure out these margins instead of going directly to the Nyquist and then back. So now, how would you figure this out? So clearly, you see this -1 0 point is the action the unit circle is the place where all the action is happening. So we'll have to keep a close eye on what is happening around the UGB, because when you are cutting the unit circle, essentially you are cutting the you are hitting the UGB of the loop. So now let's switch back to Bode completely. So let's say you have a second order system or maybe a third order system. Okay. And this is, let's say you have figured out this is omega U loop. And let's assume this is again A naught by okay. So what is the first thing that you will try to figure? Where it cuts the unit circle. Means in Bode's terms, it means you have to figure out the location of omega U loop. Okay. So now if you are only given this transfer function, the first thing that you have to do is to figure out what this Bode plot looks like. Okay. So now how will you go about figuring this out? Because you don't really know by looking at the transfer function where exactly is your omega U loop, right? So how will you figure that out? What will be your strategy? Let's take an example. Let's say A naught is 10 power 4. Okay. So A naught is 10 power 4. P1, let's say, is 10 power 3. P2 is 10 power 8. And P3 is 10 power 9. This is radian per second. So how will you go about figuring out whether things are, where is omega U loop? What will be your strategy?
After drawing the plot, you can check the P0 in P, and then from there you start 20 degree.
Okay, so now I agree. So let's assume we have drawn this plot. So when you are drawing this plot, how will you figure out where do you put this line? Right? So how do I know whether my UGB is at minus 20 dB per decade slope, or minus 40 dB per decade slope, or minus 60? That's essentially the question, right? I don't have a computer to sit. I have a computer, but when you're doing a hand calculation, you don't have that luxury, right? So what we do is again go back to the Bode approximation and then say that we will assume something and then see whether the assumption is correct or not. So what is the first assumption that I will say? I'll say the easiest one to see is that, easiest assumption to make is that, let's see, assume initially my omega U loop falls in the 20 dB per decade slope. That is P2 and P3 are beyond omega U loop. Okay, so this is assumption 1. So assume omega U loop is less than P2 and P3. Okay, so if you do that, then my Bode approximation becomes simpler, really simple. So what will be, around omega U loop, what will be the transfer function? So essentially it becomes A naught by, I can ignore these two and have 1 plus S by P1 term only, and 1 plus S by P1, I can assume it to be S by P1 and say that this is P1 by S. This has to be equal to 1. Okay. So if this becomes, S is becomes omega U loop, is how much then? 10 power 7. So this assumption becomes valid, right? So if the assumption becomes valid, you don't need to proceed any further to figure out what is omega U loop. If the assumption is invalid, I mean, for example, if my P1 would have been, I don't know, let's assume the P1 would have been 10 power 2, right? Sorry, 10 power 5. Then clearly this assumption wouldn't have been valid. Then you would have to say that I will go to this, I will take the second term into account, and then my, what would have been the expression to figure out what is omega U loop? Right, so A naught S by P1 times S by P2, which means A naught P1 P2 by S squared, A naught P1 P2 by omega U loop squared equal to that, and from there you figure out what is omega U loop. Right, so that's how you go ahead and incrementally, I mean, you keep on seeing whether the assumptions are right or not.
Since P3 is close to P2, in that case, we don't have to include the P3.
We'll see, right? So you keep on doing it. It's quite possible that P3 is also inside omega U loop, right? So that's case to case basis. So you have to figure out doing your calculation whether that is true or not. Okay. So now, so this is step 1. So you figured out what is omega U loop. What is step 2? From Nyquist, what am I looking at? At what angle I am cutting the unit circle. So which means that I need to figure out what is the angle at omega U loop. Right? So find angle at omega U loop. Find angle of L at omega U loop. Okay. So now your expression is your L of S okay. So what is the angle at any frequency omega? Angle at omega U loop will be then minus tan inverse omega U loop by P1 minus tan inverse okay. So now in a step, assuming you are interested in a stable system, what do you think the location, the relative difference between omega U loop and P1 is? I mean, the ratio, much more than 1, less than 1, approximately equal to 1. You want, you basically, you are looking for something like this system, right? So which essentially means that your omega U loop is much smaller, much higher than P1. And this assumption you also don't have to make. You can literally look at it and tell me. In this particular case, your omega loop is 10 power 7, your P1 is 10 power 3. So omega loop is like 10, but this ratio is 10 power 4, right? So which is very close to minus pi by 2, tan inverse of that. So this generally for a stable system, I mean, something that all pole stable system that you are looking for, this becomes minus pi by 2 minus tan inverse. What is this ratio? Omega loop by P2 is how much now? 0.1. Right? That's what we said, right? Yeah. And the other one is minus 0.2. Can you tell me what will this be? If you can have a calculator or Google it and tell me what is this? Sorry, 0.01, right? Sorry. Yeah, thank you. Okay, so that is essentially an excess phase of minus 5.1. Yeah. So that is, this is 5.7, is it?
0.09.
Yeah.
And this is 0.01.
Tan inverse of minus 0.1 is how much?
0.09.
Okay, so that is, I mean, obviously tan inverse of minus 0.1 is minus 0.1 approximately. Tan inverse of, right? So in terms of pi or rather in degree, you can tell me, minus 6.
In degree 0.1. In degree 5.7.
Yeah, approximately, let's say 6. So this is minus 90 minus 6 degree. Okay, so which essentially means that, let me sketch it here itself. I am cutting the unit circle somewhere here. So this is 6 degree, extra 6 degree, which means the phase margin is how much? Phase margin is 84, right? So your phase margin is 84 degree. Okay. So any questions till now?
This phase margin also taking up the degree feedback in the first thing, right?
You mean whether system is stable or not?
So because if you go towards the minus 1 flat,
Yeah.
then this our negative feedback is making weaker and weaker.
Why? What do you mean by weaker?
Because we are going out of this stability. Because
No. Okay, you have to define what you mean by weak. You mean unstable? It's going towards instability? Yes. That is definitely definitely is the case. But when you say weaker, it doesn't really mean that. You can have very strong feedback. Strong feedback means what? You can have high loop gain. Right? Strong feedback essentially means you have high loop gain. So where do you want to have the strong feedback is important. You don't want to have very high loop gain when you are hitting a lot of excess phase, right? So because what essentially he is trying to point out is another way of looking at the same thing, whatever we have been talking about in terms of margin, is what happens if P2 comes inside UGB? If P2 comes here, then essentially what we are seeing is that you have high loop gain at P2, right? So, and whenever you are hitting a pole, you are having an extra minus 45 degree, assuming that pole is, I mean, there is no pole nearby, you are hitting an extra phase lag of minus 45, which means your Nyquist plot is going closer and closer to the minus 10 point from outside the unit circle, because you have high gain, right? So you don't want to have poles at high gain, extra poles at high gain frequencies, which is essentially another backhanded way of saying that I want a first order response around UGB. Because if you have a second order response around UGB, then naturally you are saying there is another pole which is at high gain, which means you are compromising your stability, because your Nyquist plot is going closer and closer to the minus 10 point. Okay, so that is why, I mean, in the last class, I think I referred to this earlier also without substantiating it, that why we want minus 20 dB per decade roll off around UGB. This is essentially is the reason. If you can ensure minus 20 dB per decade roll off around UGB in an all pole system, then you are kind of certain that your system will be stable. Stable means without considerable ringing. You don't want a system to be marginally stable with a phase margin of 1 degree or something, right? So then it's of no use anyways. Okay. Any questions? So in essence, the conclusion from here is that you can have any pole system, but you can still make it stable as long as those poles are not affecting your Nyquist plot outside the UGB. If the poles are way outside beyond your UGB, then essentially they are not affecting your Nyquist plot. Hence, you don't really bother. So now when you are faced with a system where you have, let's say, I mean, an open loop L of S, where you have multiple poles bunched together, right? Then you already know that I am in trouble, because now if multiple poles are bunched together, you will have roll-offs of higher than minus 50 dB per decade, which means you have to come up with strategies to make them apart, push them. Pick one pole and push it to lower frequency, right? So as to ensure that omega U loop, around omega U loop, you have minus 20 dB per decade roll off. So that naturally means that your system will become slower, because you are pushing poles at lower frequencies. Your omega U loop is also going to lower frequencies. That is, in my opinion, that is the sole negative thing about negative feedback. Everything else is positive, right? Yes.
So, what is the advantage of this Nyquist over because most of the things are exactly similar, because where will be
Yeah. I mean, you can basically look at, so there are certain things which you cannot conclude from Bode plot. Like if you don't have a priori information about Nyquist, for example, it's possible to have multiple poles, and it's possible to have scenarios in which you have multiple poles below UGB and system being still stable, provided you have zeros. Okay, so you can have I mean, for example, if I just tell you, I have only observed one point, one frequency point, and I say L of S, some frequency point is minus 100. So can you tell me whether the system is stable or not? You cannot actually tell, because I have not given you any information. So it's quite possible. So what is L of S to be minus 100 means? It essentially means that you are somewhere here, which essentially means that all information you have, you are cutting this point. In an all-pole system, this definitely is unstable, but it's quite possible the system comes back and does this. When you have multiple zeros, then it will become stable. So these information are slightly difficult to, I mean, you can still get it from Bode, but interpretation becomes slightly more difficult if you don't have that assumption at the back of your mind that you have, it's basically Nyquist that pulling the strings. Okay, so that is one. And the other thing is, Bode is useless if you have complex poles. You don't have the straight line approximations are invalid, but Nyquist is always there. Yes.
Around that, when we have 20 dB roll-off, so is there any approximation of how much that, like, for how many degrees that roll-off should be there? That can create the high frequency pole after.
Yeah. So okay, so that's the next thing, right? So this is all as far as analysis is concerned. So now when you are faced with synthesis, that is, you have to figure out what is it that you need to, I mean, where do you need to place the poles, right? So that's where the next step comes in. So what is the next step? So I will cheat a bit and say that if I have any ordered system, okay, so step one is I will say that I know how a second order system behaves. I know what is the location of a second poles in a second order system, which will ensure that my system is stable, or let's say with critically damped, right? Zeta equal to 1. I know what is the location. So I will figure out what is the phase margin for that particular condition. And then I will say that for any ordered system, if I satisfy that phase margin, my system will behave similarly. So that is strictly, again, not true, but to a certain degree of approximation, that's a mathematical assumption that we make. So which essentially brings me to that point, that what is the phase margin for critically damped system? Okay, so what is the phase margin for critically damped system? Can you now tell me? I mean, when I say it's critically damped, what is the assumption that I am making with respect to P2 and omega U loop? So am I making the assumption that my P2 is beyond omega U loop, or am I making the assumption that P2 is before omega U loop? Which assumption am I making for critically damped? If you are not
So
sure,
critically damped means system is
zeta equal to 1.
zeta equals to 1, but in terms of settling time, I mean it's a slower system, right?
Okay. Yeah.
So in that sense, the bandwidth will be small.
Okay.
So I think the this one,
Black one.
no,
This one. Okay. So okay. So can you make an assumption on bandwidth based on this now? That's also a good question actually. So when you have, let's say you have a marginally stable system where zeta equal to 0. Okay. What will this Bode plot look like? It will look something like this, right? So you'll have poles at very low frequencies, right? Last class, what you saw is that if poles are at very low frequencies in a high gain system, your zeta almost goes to 0, right? So which means you will have probably some roll off like this directly.
But when the zeta is 0, that is it has a complex pole, right?
Yeah.
So in that case, how is Bode plot?
So zeta is complex pole in which domain? In L
domain.
No. Is it in L domain or is it in the closed loop domain?
In the closed loop domain.
So Bode plot is not for closed loop domain, right? Bode plot is for L domain. Right. So we are trying to make an assumption. We are trying to figure out how the closed loop system will look like looking at the open loop system. Right. So that's essentially the theme of the course. Okay.
Complex poles will be having whether peaks or not.
Complex poles you will be having in the closed loop domain, not in open loop. Right. So I can have my open loops, for example, L of S to be equal to omega u squared by S squared. Real pole at 0, right? So I'll have, this should look like this, right? So this will be omega u. In the open loop domain, in a closed loop, this is an oscillator, right? 1 plus omega u square plus S square. So clearly at omega equal to omega u, you have infinite gain, you have complex poles, it becomes oscillator in the closed loop. So again, so this initial assumptions that we did that UGB in the open loop system translates to 3 dB of closed loop system for a first order system, right? Not for a higher order system, but it's still an approximation that is valid as long as it looks like a first order system around the UGB, right? So it's basically boils down to this condition that around the UGB, if it's a first order system, I can neglect these two terms. Then it becomes first order, then the properties of first order system are more or less still valid, right? So yeah, so that's what we call dominant pole. Okay. So when you have, this information doesn't really convey what the bandwidth of the closed loop system will be, because in this case, where are you cutting in the magenta case? Where are you cutting the unit circle? Before P2 or after P2? After P2, exactly. So you have high gain, right? So your units, your Nyquist plot will go closer to -10 point, right? So which means you will have more instability, more ringing. So this definitely cannot be a marginally stable case. This definitely cannot be a critically damped case.
So more ringing in the closed loop system. Right?
Yes.
And so the zeta equals to 0, you are saying that is basically you are giving the information about the closed loop system.
Yeah, obviously, right? So if you go to the derivation, it's basically how do we come up with zeta? We had that L of S, we put it in 1 plus L format, and we found out zeta, right? So you don't even have to make these assumptions. You can directly look up tell me what is the P1, P2 relation in a second order system. So look, tell me, look into your previous lectures and tell me. Assume P1 and P2 are far apart. So first thing, what is omega u loop? For critically damped, right? This is for critically damped. A naught P1. For zeta equal to 1, what is the relation between P1, P2, A naught? So what will be the phase margin for this case? So minus pi by 2. What is the excess phase at omega u loop? So minus tan inverse omega u loop by P1 minus tan inverse omega u loop by P2. Okay, so this is approximately minus pi by 2 minus tan inverse 4, right? So tan inverse 4 is approximately 14 degree because I remember by heart. So this essentially you get about yeah. So yeah. Sorry. Correct. Thank you. Because 1 is itself minus 45, right? So 45. So essentially, what we are seeing is this is approximately. So what is the margin now? Margin is phase margin is how much? Phase margin is you take this entire thing minus of minus pi. So pi by 2 minus tan inverse 1 by 4. This is 76 degree approximately. Okay. So essentially in the unit circle, you mark off a minus 76 degree point. You are entering the unit circle at this location. This is for second order system. Now for higher order system, we say that we will cheat and say that, okay, it doesn't matter whatever is the, how many poles you have, as long as you can hit this phase margin, you will have similar response, which means that I can have a higher order system which enters through here, and you can have multiple poles, and it can go like this, it can go like this. What I am postulating is these two curves in the time domain, the response of the system will be identical, which is strictly not true because obviously two different, I mean, inverse Laplace of completely two different polynomials are never identical. I mean, almost never identical. So, but still this is, I mean, as far as the step settling is concerned, that is with respect to ringing and all is concerned, this is something a pretty well accepted approximation, and that's what we generally do. Now, coming back to his question, so this essentially gives you an idea of how far the P2 will be for in a second order system with respect to omega u loop. P2 has to be 4 times omega u loop in order to have critically damped condition. Now, let's say assume you have a third order system and you want to mimic this critically damped condition for a third order system, right? So which essentially means that for third order, you will have this angle to be minus pi by 2 minus tan inverse omega u loop by P2 minus tan inverse omega u loop by P3. Now, in a third order system, you are constrained with the fact that the excess phase lag due to these terms has to be 14 degree. So in the second order system, only one term could have, only one pole could have, it would have been okay for only one pole to give you that extra 14 degree. But in a third order system, now you have this extra 2 poles. The summation of the phase lag of those 2 poles at omega u loop has to be 14 degree. Okay, so which means that this individually, this P2 and P3 have to be lower or higher with respect to the second order case at a higher frequency, right? So with if in a second order case, this my P2 would have been okay if my P2, so in this case, basically my P2 is at 4 times omega u loop. to satisfy the same condition, in this case, my P2 and P3 has to be at even higher frequency than the second order case, because I now two terms should coalesce and give you 14 degree. In the previous case, only one pole was giving you the excess phase. Okay, so which essentially means that if you have to mimic the response of a second order system and a third order system, I mean, rather, if you want to mimic the response of a third order system like a second order system, you cannot leave this P2 at this position. So let's say you assume you want the same omega u loop, which means in a third order system, this modified P2 has to be somewhere here because you have another P3. So this becomes, so this will become something like this, right? Because this is obviously not visible. I mean, the effect of this is obviously not visible in the Bode domain, because in Bode domain, unless you hit the pole, nothing happens. But in phase domain, you will see, you should be able to see. If you see the phase in Bode magnitude domain, right? So this is in Bode phase domain. In the phase domain, you start off with, let's say, 0. Then you hit here, then you hit another, go to minus pi by 2 in case of second order, but in case of third order, so you will hit slightly extra phase because you have another P2 lurking somewhere nearby. Then you have another P3, then you go something like this. So this extra stuff can cause problem if you don't move, right? So essentially you'll have to move this phase to a higher frequency. Rather, you have to move the pole at higher frequency so that you get the same phase lag with respect to the second order system. So it will be something like this. Horrible drawing, but you get the point, right? So hopefully. Okay, any questions? I realize that this is too fast, right? Because I made a lot of assumptions that you know Nyquist, you have done those courses and all. But that's a fair enough assumption, right? You have done those courses. Okay.
Then if you have 4 system, then you have to that extra frequency can again distribute it.
Yeah, right. If you have 4 extra, exactly. So you have that bucket of extra phase. Now, if you have more poles, you distribute it among them. That's why if you have higher and higher poles, you'll have to ensure those poles are so far apart they don't cause any phase lag, any substantial phase lag at omega u loop. If you cannot do that, the only thing you can do is move omega u loop lower. Otherwise, you will have instability. So that's why more poles makes your system slower, not because that you cannot make a faster system. It's essentially you cannot make a more stable system. Stability and requires that you'll have to ensure poles become, usually becomes comes at a lower frequency. So intuitive way of understanding this is from the delay picture. I don't want to go into delay picture because that itself is 2 classes. But if you think about it, a phase lag is similar to a delay, right? It's equivalent to a time delay. It's an approximation. A phase delay is equivalent to a time delay. So now in a negative feedback system, if the feedback information comes after some delay, then obviously your action, the corrective action will also occur after some delay. Okay. So if there is a difference between when the corrective action should have ideally happened and when you are taking the action, then it's possible that the integrator would have overshot. Right? Think of when you are driving a vehicle and your brake is bad. Right? So you are supposed to, you found somebody in front of you, you braked. But the brake actually is so bad that the effect of braking comes after a long time. Then you will obviously go and hit that person. Right? Because the feedback that you got, you have to stop, and the action that you took was delayed. Even let's say you are driving in the dark, you drive slightly slower because you know that I cannot see at a longer horizon, because the feedback that I am getting is slightly delayed because of the environment. So you are essentially slowing your system down for the purpose of safety or stability, right? Because if you slow it down, you have longer time to make a correct decision. Because if you have delay, then you might take up a wrong decision. You might go in a different direction. So essentially, that's what your electronic system is also doing. If you have a delay, you have a problem. If you have a delay, the only way to make things stable is slow down. Okay. Okay, fine. We'll see you in the next class.